Welcome back to Dave Does Math from Home. This is the fourth and I assume final installment of our video series about flux integrals, and in this one, buckle your seatbelts because we're about to do the flux through a sphere, specifically a half sphere. I imagine that this problem has something to do with drain catches. That's how I like to think of it. We want the flux of the rain vector space. So the vector space is just going straight down everywhere. This is f equals 0, 0, -1. That's our vector space. It's going down everywhere. And it's through a half sphere of radius 2 oriented downwards. So I like to imagine this as like when you're taking a shower or a bath and things go through the drain. There's a drain pipe. Water is flowing downwards. Maybe you have some sort of dome sphere-shaped like drain catch in there to catch hair or other things from flowing too far down the drain. But water needs to flow through this grate, this metal mesh that's in your drain. So we're going to pretend that this is the bottom half of a sphere and things are flowing through it downwards. And we're going to find the flux of this flow through this surface. The very exciting part of this is going to be parameterizing this surface. Parameterizing a sphere is an ordeal. So bear with me. I'm probably going to have to erase the board at least once. Write this down. Just like when we parameterized the cylinder in the last example, and we leaned very heavily on our knowledge of cylindrical coordinates, here we're going to do the same thing. If we want to parameterize a sphere of radius 2, we said, we need to rely very heavily on our knowledge of spherical coordinates. In spherical coordinates, we had these relationships. X equals rho, sine of phi, cosine theta. Y is rho, sine of phi, sine theta. And z is rho, cosine of phi. These are our spherical to rectangular transformations. If we fix the radius at 2 and we let phi and theta vary across whatever they normally vary across, that's how we parameterize the surface of a sphere. So it's big and it's kind of messy, but it gets the job done. Maybe I shouldn't say elegantly. It gets the job done, I will say that. So x is going to be, we're fixing rho at 2. So x is going to be 2 sine of phi cosine theta. Y is going to be 2 sine of phi sine theta, and z is going to be 2 cosine phi. This is the parameterization that we want to use. And if we want this to be the bottom half of the sphere, we need theta is going to go from 0 to 2 pi, and phi is going to go from the bottom half of the sphere. Is phi is going from pi over 2 is horizontal on phi, and pi is straight down on phi. Remember, phi is the one that, phi doesn't do full rotations all the way around. Phi only does half rotations. 0, phi equals 0 is straight up, phi equals 90 degrees or pi over 2 is straight horizontal, and phi equals pi is straight down. And that's the full range of motion on phi. So if we want the bottom half of the sphere, we're going from pi over 2 to pi. So this is our half sphere. We need to take derivatives of this, and then we need to take the cross product of those derivatives. So I need the derivative with respect to phi. We'll start with phi. Derivative of this with respect to phi is going to be sine of phi is going to turn into cosine of phi. Theta will remain unchanged. So 2 cosine phi cosine theta. Derivative of this is 2 cosine phi sine theta. These need to go away, so I have space. Derivative of this with respect to phi is negative 2 sine of phi. Derivative with respect to theta here. We're going to have negative 2 sine of phi sine of theta. This one is going to be positive 2 sine of phi cosine theta. And this one is going to be 0. Whew. Okay, we lucked out on one of these. We got 1, 0. The more zeros you have in this chunk, the easier the cross product is. I think I'm going to start erasing things already so that I can make this cross product fit. So this is a parameterization. Remember this. I'm going to erase it so that I can put the cross product here. We can rewrite it if needed. Okay, the cross product, N, is going to be the determinant of this and this. Yeah, no, the commas can stay, I guess. And we'll use an I and a J and a K. Bam. Instant cross product. So when I expand across I, I'm going to have 0. I will have negative 4 sine. Oh, sorry. I wrote this wrong. This should be sine of phi. Ugh. See how easy it is to just make a tiny mistake and then ruin things? I'm glad I caught that. This should definitely be the sine of phi because it is the derivative of cosine of phi from that thing that I just erased. Anyway, we expand across I. We have 0 minus negative 4 sine squared phi cosine. So this will be, the negatives cancel, and we have 4 sine squared phi cosine theta, comma. When I expand across J, I'm going to have 0 minus positive 4 sine squared phi sine of theta. But remember, J is the one that's sort of inherently negative, so it's positive. It's the backwards diagonal, so that's negative, and then it's J, so it's, okay, it'll be positive. Positive 4 sine squared phi sine of theta. When we expand across K, we will get 4 cosine phi sine of phi cosine squared theta. Sine phi cosine squared theta minus negative, so positive 4 plus 4 sine phi cosine phi sine squared theta. Okay, so this was a lot of cross product, but we can simplify this a little bit, and then after we simplify it, we're going to multiply it by a really nice vector space. It'll clean things up nicely. It's not as bad as it looks. Trust me. When we simplify this, we're going to get, this piece doesn't really simplify. It's just going to be 4 sine squared phi cosine theta. This will be 4 sine squared phi sine theta. And this, if we factor out the 4 sine phi cosine phi, each of these pieces has a 4 sine phi cosine phi in it. If we factor those out, then what's left is cosine squared plus sine squared, which is just 1. So this is 4 sine phi cosine phi times 1. So it does clean up a little bit nicer than how it originally looked. Still kind of crazy looking, but it's the kind of crazy looking that we can deal with. I'm going to erase things now. I'm going to erase like the entire cross product stuff. This is no longer needed. I have my n. Do not need the matrix from whence it came. So this is step 2. Let's go to step 3. Step 3 is we need to write f in terms of the parameterization. I've already erased the parameterization, but it's fine because f is all constants, and so it's not going to change. So f is 0, 0, -1 still. That hasn't changed. Step 4 is I need to do the dot product of f dot n. And that dot product is going to be 0 plus 0 minus 4 sine phi cosine phi. Oh, I forgot to check if this was actually oriented in the right direction. So we want this thing oriented downwards. So let's just pick a point here. Let's say when phi is pi, what is this value? Is this positive or negative? Oh, that would be 0. Why is the normal vector 0 at the bottom of this thing? Let's pick something more in the middle. Let's pick 3 pi over 4. When phi is 3 pi over 4, that's like this angle downwards. And this will be sine of 3 pi over 4 is positive, cosine of 3 pi over 4 is negative. So, yeah, this should be pointing downwards at 3 pi over 4. Why is it 0 when Huh. Oh well. Okay, so it's oriented in the correct direction, and I have the dot product of my normal vector is negative sine phi cosine phi. So last step is I need to take the integral of this dot product, negative 4 sine phi cosine phi. Let's do d phi first and then d theta after. With d phi here, we're going from pi over 2 to pi. And on theta, we are going from 0 to 2 pi. So hopefully we remember that the integral of sine phi cosine phi is 1/2 sine phi squared. So we can do that. 0 to 2 pi, negative 2 sine squared phi not from 0, from pi over 2 to pi d theta. So when we evaluate this at pi, we're going to get this evaluated at pi is 0, minus, when you evaluate this at pi over 2, that's 1. So 1 squared is 1, minus negative 2. So plus 2 d theta. And the integral of 2 d theta from 0 to 2 pi is 4 pi. So the flux through the drain catch of the flowing water is 4 pi. That was a 15-minute problem, largely because parameterizing spheres and then finding normal vectors to them is a little bit obnoxious, but it's very doable. So I hope that you have enjoyed this thing. That's going to do it for these videos. I think these videos are a pretty solid foundation for doing the homework problems. The homework problems are a little rough, so I tried to find ones that would sort of ease you into flux integrals as best they could, but at this point in the book writing, I think the authors have sort of just lost their minds and only exist as generators of absurd problems. So we'll definitely talk about those in class. Try them out when you get a chance and ask me really good questions, and we will get through it. And then the good news is we're going to learn some shortcuts to do these things easier starting in the next section. So stay tuned for that. It'll be a good time. We'll see you in the next one.